Hello there guys, and welcome back to another epic intellectual maths video. In this video we're looking at proving some identities of hyperbolic functions. So this video may be slightly longer than normal. We're going to try to prove some of the identities. I shall leave the timestamps in the description and in the comments section, so you can skip to them if you want to only look at a few of them. But we're going to look at some various hyperbolic function identities. Okay, so there's a lot of them. There's an awful lot of them. In fact, there's just as many of these guys as there are for the trigonometric ones, the corresponding ones. So I'll show you some of the ones that I've written down here. As you can see, we've got ones that we've already seen before. So tan x equals sin x over cos x. We've seen that one already. A few others, cosec x equals 1 over sin x, sec x equals 1 over cos x, etc. We've seen these before, but all of the others we have not seen. So we have not seen cos squared x minus sin squared x equals 1. We have not seen 1 minus tan squared x equals sec squared x, etc. There's also, and I'll move just the page slightly over here so you can see it a bit better, but also we have got the addition formulae, or the compound angle formulae here for sine, cos and tan, and they're written here, and also the double angle formulae for sine, cos and tan. Of course, just like with trigonometry, these are not the only identities that exist, but these are the main ones. These are the most important ones, arguably. So we're going to look at proving as many of these as possible, okay, in this video. And in general, as a general rule, if you don't need to memorize these, because you say, well, they look kind of similar to the trig ones. They are very similar to the trig ones. If you actually look at this, you might notice that some of them are the exact same, just in hyperbolic form. So for example, if we look at the double angle formula for sine of 2a, we end up getting that sine of 2a is actually identical to 2 sin a cos a. But sine of 2a is 2 sin a cos a. So actually this is exactly the same as its trigonometric counterpart. However, if we look at cos 2a, it's not the same, because cosine 2a is cos squared minus sine squared, but cos 2a is cos squared plus sine squared, so it's not the same. So some of them are the same, some of them are not the same. There is a nice rule that we will look at in a separate video, but I will introduce it to you now. It's called Osborne's rule, and what it states is that if you want to know what the hyperbolic identity is that relates to some trigonometric one, then you just take the trigonometric version, and it's the exact same as the hyperbolic version is the exact same as the trigonometric version, but if in the trigonometric one there is a sine squared, or if there are two sines multiplying, then you need to change the sign in front of the sign, if that makes sense. So if you have a sine squared in the trig version, in the hyperbolic version it goes to a minus sine squared. If you have a minus sine squared in the trig version, it goes to a plus sine squared, but everything else is the same. That's why in cos 2a you get cos squared a plus sine squared a. Normally there's a minus sign there, but it changes to a plus because it's a sine squared. You'll also notice in the very first one here, the cos squared minus sine squared equals 1. The trigonometric version of that is cos squared plus sine squared equals 1. But because it's a sine squared in the trig version, the hyperbolic one corresponds to a minus sine squared. Okay, but you can actually prove them straight up just using their exponential definitions, which is what we're going to look at right now. So the first one that we want to look at is going to be proving that cos squared x minus sine squared x equals 1. Okay, this is the first one that we want to do, or rather that it's identical to 1 actually. So how do we do this? Well, we take our definitions of cos and sine. So cos, remember, is e to the x by definition plus e to the minus x over 2. This is cos. So cos squared is just all of this squared. And then we're going to take our minus sine, so minus sine squared. Well, sine is e to the x minus e to the minus x over 2. And what we want to do, and we're going to square this as well because it's sine squared, we want to make sure that this is equal to 1, or that this is identical to 1. We want to show that the left-hand side here is identical to 1. So all we do is we expand all of this out. So this is e to the x plus e to the minus x squared e to the x plus e to the minus x squared divided by 2 squared, which is 4, minus e to the x minus e to the minus x all squared divided by 4. And we're still checking. Is that equal to 1? Not sure. Let's keep going. So expanding this top bracket out, e to the x squared is e to the 2x. E to the x times e to the minus x is 1, and that happens twice. And then e to the minus x squared is e to the minus 2x, and that's still just divided by 4. And then we're going to take away the same thing, so e to the 2x, and this is going to be minus e to the x times e to the minus x, which gives you minus 2, because it happens twice. And then you get plus e to the minus 2x. And this is still divided by 4. Okay? Right, now if we clean all of this up, we have got that we end up with 1/4 e to the 2x plus a half plus 1/4 e to the minus 2x minus 1/4 e to the 2x plus a half. Because this is a minus sign here, it needs to distribute to that minus sign there, so we get a plus half there. And then we're going to minus our 1/4 e to the minus 2x. That is identical to 1. And then we can clean this up by quite a lot, and everything should more or less cancel out. So we get 1/4 e to the 2x cancels out with the minus 1/4 e to the 2x. 1/4 e to the minus 2x cancels out with the minus 1/4 e to the 2x, e to the minus 2x. And we just get left over with a half plus 1/2, which is 1. So 1 is identical to 1. Therefore, we've proven the identity that cos squared minus sine squared is identical to 1. Okay, that one has been proven. Okay. The next ones that we're going to look at are the ones that basically come from that formula. So if we go with our cos squared x, we'll just do this. So we're going to prove the identities right now, but I'm going to start off with a different identity to show this. So cos squared x minus sine squared x is identical to 1. Okay, and if we're going to prove two identities right now. If we divide everything in this equation by cos squared, dividing by cos squared, we end up getting 1 minus tan squared x is identical to sec squared x. And if we divide everything by sine squared, we get coth squared x minus 1 is identical to cosec squared x. So these are the two other identities. You might recognize their trigonometric versions as well. So you'll notice again that these are the same as the corresponding trigonometric ones, with one difference. The difference is when there is an implied sine squared, because tan squared is sine squared over cos squared. So normally this is 1 plus tan squared equals sec squared, right? But it's 1 minus tan squared in this one, because tan is sine squared over cos squared. So the sine squared makes the sign change to a negative. Even though sine is not explicitly in that equation, there is an implied sine squared in there. So you get these two identities as well. That's those two ones proven. Okay guys, so the next set of identities that we want to look at are the addition formulae. So the addition formulae for sine of a plus b is sine a cos b plus sine b cos a. This is the exact same as the trigonometric version because there's no sines multiplying together. There's no sines multiplying together, so it's the exact same. So how do we actually prove this? Well, we can again use the exponential definitions. Let's start off this time with the right hand side, and let's try and rearrange to get to the left hand side. So if we use the right hand side, sine a cos b, this gives us e to the a minus e to the minus a over 2. That's the sine a, multiplied by cos b, which is e to the b plus e to the minus b over 2. And then we're going to add sine b, which is e to the b minus e to the minus b over 2. And that is being multiplied by cos of a, and you can probably in the way at the moment, but yeah, cos a, and cos a is equal to e to the a plus e to the minus a divided by 2, just like that. Now, if we clean all of this up a little bit, and we want to, by the way, we want to show this is equal to sine of a plus b. That's what we're trying to do. So if we clean this up a little bit, we'll get, and expand all of this out, we get e to the a plus b, multiplying e to the a and e to the b together. And then outside, so e to the a times e to the minus b gives us e to the a minus b. Inside gives us minus e to the minus a plus b, and then the outside gives us minus e to the minus a minus b, and that's all being divided by 4. That's the first one, okay? Just using FOIL, expanding out. The next bit is going to be plus e to the a plus b. Outside is going to be plus e to the minus a plus b. Inside is going to be minus e to the minus b plus a, and then finally on the outside, or the last, sorry, we've got minus e to the minus a minus b. And again, that's all being divided by 4, okay? All being divided by 4. Now, if we divide it all by 4, we do all of this, we can collect up the numerator. They have the same denominator, so the numerators can all be the same. So rounding this all up, we have an e to the a plus b plus another one of those, if you can see that. So giving these the same numerator, we can say that we have 2 times e to the a plus b. And as we go, I'll cancel these out. So we've dealt with that one, we've dealt with that one. It's 2 e to the a plus b's. We now want to gather up all of the a minus b's, if there is any. There is a minus b plus a, that's the same thing. So e to the a minus b cancels out fully with e to the, this is basically an a minus b, it's minus b plus a, they're the same thing. Okay, also minus e to the minus a plus b cancels out with plus e to the minus a plus b, so they cancel out. And then we also have a minus e to the minus a minus b minus another e to the minus a minus b. So they don't cancel out, they actually add up, and we end up with minus 2 lots of e to the minus a minus b. And this is all still divided by 4. And then this is identical if we divide the numerator and denominator by 2 to this. E to the a plus b minus e to the minus a minus b. And of course this is very nice because we can write this as e to the a plus b minus e to the minus a plus b, so factor that out in the numerator, all divided by 2. So what is this though? What is this? This looks very familiar. Well, actually this is just sine of a plus b, isn't it? It has to be. E to the a plus b minus e to the minus a plus b over 2. If a plus b were an x, it would be e to the x minus e to the minus x over 2. So replacing x with a plus b, you get sine of a plus b. That's the addition formula for sine of a plus b, proven using exponentials. You can also do this with cosh and than. We won't do it. It's the same idea. If you do this with cosh, you can then work out the one for than by either using the identity again or just doing the sine one divided by the cosh one. And actually, yeah, indeed, you'll get the one for than as well. Now, we also want to look at the double angle formulae, of course. So the double angle formulae, these are the double angle formulae. Okay. Now, the double angle formulae, just like the trigonometric versions of these guys, also just come from the addition formulae, just letting a and b be equal. So if we take our sine of a plus b, which we already know what it is, it's identical to sine a cosh b minus sine b cosh a. And by the way, guys, if you wanted a sine of a minus b, then all you would do is you would replace b with minus b. That's actually meant to be a plus. You'd replace b with minus b. So you just put a minus in there, and you put a minus in there. And the thing is about this is that because cosh is an even function, and we'll talk about, if you know what an even function is, that's brilliant. Cosh basically has this identity, just like cos, where cosh of minus x is the same thing as cosh of x. So on the cosh, b being minus b does not change it, so it just stays as that. And shine of minus b, you can have this identity where shine of minus x is equal to minus shine of x, just like with sine. So this minus can distribute out and it can become a minus there. So if you have shine of a minus b, then the minus sign just goes in front like that. And you can use similar logic with cosh. So if we use this and we want to derive the double angle formulae for shine, we just let b be equal again to a. And that means that we get shine of a plus a, so let just b be the same angle. This is identical to shine a cosh a minus shine a cosh a. Amazing. Okay, so it's supposed to be a plus. Okay, and then shine of a plus a, that gives you shine of 2a. And this is identical to shine a cosh a plus shine a cosh a gives you 2 shine a cosh a, which of course is the double angle formula for shine. And it's, again, there's no shines multiplying together, which means it is truly the exact same as the trigonometric version. Okay, last but not least, let's do the double angle formulae for cos or cosh. So we know the cosh of a plus b is going to be equal to cosh a cosh b plus shine a shine b. And this one is slightly different to the trigonometric version because the trigonometric version has a minus sign here. There is a minus sign there, whereas the hyperbolic one does not have a minus sign. The reason why the hyperbolic one does not have a minus sign is because it's 2 shines multiplying together, which creates the negative sign that goes in front of the negative sign that was already there, making it positive, just like what we've got right now. So this is the identity for shine. Amazing, amazing, amazing. For cosh, sorry. So how do we do this? Well, again, we let b just be equal to the same angle as a, and then we get cosh of just a plus a is identical to cosh a cosh a plus shine a shine a. Okay, now that means that cosh of, and again that was supposed to say cosh of a plus a. Cosh of a plus a, as we know, is just cosh of 2a, and this is then identical to cosh a, that's cosh squared a, of course, plus shine squared a. Brilliant. And this is one of the formulas for cosh of 2a. Of course, just like the trigonometric version though, there are actually 3 different double angle formulas for cosh of 2a. So we can use, and I'll write this down in purple as a little side note, an identity that we've already derived, which states that cosh squared of a minus shine squared of a is identical to 1. We can use this and do some rearranging. We end up getting that cosh squared of a on its own is identical to 1 plus shine squared of a. And we also get that shine squared of a is identical to cosh squared of a minus 1. So using those 2 facts there at the bottom, we can take our cosh 2a identity and we can say that cosh 2a is also, you can, depending on the situation, which one you want to use, but cosh 2a is also identical to, replacing the cosh squared a with 1 plus shine squared a, you get 1 plus 2 shine squared a. It's one of them. And cosh of 2a, replacing the shine squared with a cosh squared, you end up with cosh squared plus shine squared, which is cosh squared minus 1, which gives you 2 cosh squared a minus 1. So these are also the 2 double angle formulae here, 2 more double angle formulae for cosh 2a. And again, the way that you get the one for than is by doing the exact same thing, just taking the addition formulae, the compound angle formulae for than, and replacing b with another lot of a. As I said, there are lots and lots and lots of different hyperbolic identities. It's not the only ones, there's loads of them, but these are the basic ones, these are the simple ones, and it's more just about showing you, introducing you to the idea that essentially you can prove all of these just using the exponential definitions, the e to the x minus e to the minus x over 2, e to the x plus e to the minus x over 2, etc. You can use all of these identities to prove things. There's also another way to prove these identities, which we will look at in the future, looking at Osborne's rule and things like that. But for now, thank you guys so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.